So you don't do any stimulation. So now we discuss in details of the amplifier. The amplifier is actually the core of your instrument. The amplifier takes the weak signal out of the electrodes and transform it in such a way that you can actually store it or visualize and use it for your experiment. Of course, I will not really give you the detail of circuits and things behind the amplifiers. I just want to discuss a little bit of the operational amplifier. And if you really want to learn a bit more about amplifiers, well, the Webster, the book that I put into the reference, will tell you everything you need to know. There's a lot of history behind the development of the amplifier, particularly, well, at some point when the amplifier developed, engineers and technicians, they went off and they built the bioamplifier. And that is an history and development on its own. So a bioamplifier is an amplifier that is specifically designed to amplify physiological or biological signals. And this started to develop into the 70s. So there's one little thing I want to tell you, because you might record data, particularly if you keep working as an array. Every time you connect somebody to an amplifier, do you know that you are actually putting them at risk? Well, you are. And there are some interesting readings, which I might send you the link through Yossi, that in hospitals, particularly in the 70s, a lot of patients they were dying in hospital just because they were connected to the bedside monitor. So this is another point. Don't ever use a faulty equipment, particularly if the equipment is powered by the main. Anyway, we're jumping ahead too much. So the ideal amplifier can amplify anything. That means everything is perfect. Whatever you put at the input of the amplifier amplifies it by infinite gain. The amplifier has no contact impedance issues, has infinite drive capability. That means I could drive simultaneously a paper printer. If I want to print my signal, I can drive a display. I can store the signal with no problem. Well, as an engineer, I really wish that the perfect amplifier or ideal amplifier will exist, although I understand that if such amplifier would exist, simply turning it on, or actually just the matter of fact that things could exist, it could destroy the known universe. And there is a little bit of a homework for you, how an ideal amplifier can destroy the universe, which we can discuss later, and maybe at the end of the lecture I'm going to tell you why. Anyway, the ideal op-amp, or operational amplifier, as I said, has an infinite impedance. So all the amplifiers that you're going to use, they are voltage amplifiers. Now, how do you measure a voltage? You measure a voltage putting something in parallel to the voltage you want to measure. In case of the human body, you want to measure the voltage out of the brain, the EEG. You put a bunch of amplifiers in parallel with the electrodes, or where the EEG needs to be recorded. And you wish that the input impedance of this amplifier is as high as possible, ideally infinite. You want these things as infinite because if there is another resistance connected between the pins of the amplifier, which could be the electrode resistance that we mentioned before. You don't want to change in any way that circuit. You want to observe it, right? You want to treat your signal like a movie that is happening, and you're just sitting and relaxing into the movie theater and you watch it. Okay, different is if somebody is listening music through the headphone, and the headphones are terrible, and you can hear the music. So it's the same kind of paradox. If your observer isn't perfect, or your listener isn't perfect, you're going to change the shape of the signal. Obviously, the music you hear leaking through someone else's headphone is not as good as it would be if you're listening through the headphone, right? So that's the same thing. So if the input impedance of an amplifier is not infinite or very, very high, you're going to change the behavior of the signal. And now you might start to understand things. Contact impedance of electrodes, input impedance of amplifiers. If the input impedance of the input impedance of the amplifier is not something you can control. It's been given to you. And probably you can go and check your equipment. One of the specifications that they declare is the input impedance of the amplifier, which is in the order of gigaohm or teraohm, of course, but the contact impedance is in the order of hundreds of kiloohm. And at some point, this could be comparable. So going back to the stimulation, because it's the same thing, the stimulation are actually driven by an amplifier. So they are at the other end of an amplifier. And the reason why you want zero output impedance for an amplifier or infinite drive is because you want to win, or you want to sustain that current or voltage no matter what you connect to the amplifier. A stimulation amplifier is designed to give you milliampere no matter if the skin impedance is perfect, which is about 5-6 kiloohm, or the skin is a bit not prepared well, so you have like 10-20 kiloohm. However, the thermal effect is going to change. And in case of extreme stimulation amplifier, like the cardiac defibrillator, you can actually spark the chest of a person. So the defibrillator, what actually does, it creates a current arch in between those two plates that goes through the chest and try to restart the heart. In order to do so, the voltage in between those two plates is in the order of 200 kilovolt. Okay, so it's a huge voltage. That's the reason why you can't shock a patient with a defibrillator more than 6-7 times. And most of the time, patient, yeah, okay, they get shocked, they are revived, they're happy, but they're gonna bear consequences of the burn, and sometimes internal organ burns for years or for their full life. So amplifiers are designed that no matter in which job you want to use them, they're gonna give you the best. However, they are not ideal, they are gonna be real. That means that they're gonna have a limit into their driving capability, and they're gonna have a limit into their input impedance capability. That's why your signal gets destroyed, that's why you can't stimulate with infinite current. And most importantly, you can't have an infinite gain, because that's why this amplifier, the ideal amplifier will destroy the universe. If it has an infinite gain, and the infinite drive capability, it means that every little energy at the input, and because as the infinite input impedance is going to catch energy from everywhere, is going to amplify times infinite, so it's going to produce blasts of energy, infinite blasts of energy that they can destroy the universe. We want high gain, but we don't want to destroy the universe, right? Most importantly, amplifiers, real amplifiers, they are powered by something. So into these slides, into this schematic, you don't see any power. That's another characteristic of the ideal amplifier. It doesn't require power. Well, try to record the EEG without turning on the power of your EEG recorder. Do you think it's going to record the EEG? Not at all. So the amplification happens at the expenses of the power supply. This means that the driving capability are limited as well by the power supply. So if your power supply is, say, 10 volt or 9 volt, the typical 9 volt battery, the output of an amplifier cannot exceed 9 volt. If your amplifier is gaining 1000, let's make an even number, 10 volt power supply, maximum 10 volt output, and a gain of 10. It means that if you at the input have 1 volt, you reach your maximum output. If you put 2 volt at input, well, the amplifier is still going to try to gain 10, but 2 times 10 is 20, exceeds the 10 volt. What is going to be the response of your amplifier? Flat line at 10 volt. Now things add up and you understand the issue with contact impedances and not preparing well the skin and the electrodes drift value, because the alpha cell potential of the electrodes will get amplified by the gain of your amplifier. Well, not entirely, of course. But if those things, they change, well, you see that the EEGs, they go all over the place. So you expect all the traces of the EEG to be flat and zero, right, during the recording. Are they always flat on zero? No. That is because some electrodes, they have different contact impedance. So the alpha cell potential of the electrodes is leaking through differently for all the electrodes. If one of them goes too high, well, you start to have the clip onto your signal. And that's the reason why you should always, no matter what, look at the data raw. There is nothing worse than actually presents research results of data that have been filtered, and because of the filter, they actually look good. That is terrible, and I see this happening all the time. So I want to give you a quick example of that. This is voltage, whatever it is, and that's time. And this is the dynamic of the amplifier. So the amplifier can't exceed the power supply. So if these 2 dashed lines over here are my signal, are my dynamic range of the amplifier can't go out. So say that for some reason your EEG sits on this line instead of 0, which is often the case, right? And it starts to do that. All good. Perfect. Say that during the recording, because the electrode goes loose, you still have your signal, but these things rise up here. You're still going to have a EEG. Your amplifier is going to still work, but you're going to have this. you're going to have some little brief period of flat lines only on one side of your signal. If you filter the recorded data, I bet that 99% of these periods are going to disappear. But that is an artifact. That's not signal. Whatever conclusion you draw or your supervisor draws from this signal is wrong no matter what. Why? Because you haven't prepared properly the skin. Or you haven't watched during the recording how these things was changing. What's the cause of this? A movement, particularly with children, this happens all the time. Or simple, after a few hours, the gel needs to be refreshed because it's drying out. Anyway, well, we discussed already the truth about op amps, that they are not ideal and so forth, so they can't destroy the universe, but they, unfortunately, together with the benefit of not destroying the universe, it come a lot of catches like the one that we just discussed. We discussed this already, so that the output of an amplifier can't exceed the voltage supply. Into the example I just gave you a positive voltage supply of 10 volts in the one that we discussed, but you see in what I plotted that you normally have a positive and a negative supply. That is because our signals sometimes they have negative excursion, so we want to have an amplifier that is able to follow those negative things. So the only things that makes an amplifier usable is actually the feedback, which is kind of complicated, but if you think about it, feedback is what makes the human body as well to work. Nothing is open loop. Well, do you know that actually human muscles, particularly the quadriceps and the biceps, they are so powerful that they could rip themselves off the bone if you contract them too much. Did you know that? Well, that actually is the case. Is that there are three muscles that are known that they can do that: biceps, quadriceps, and calves. Those are the most powerful muscles that we have into the body. Why they don't rip off the bones all the time? Because of the feedback. Inside the muscles there are some specific cells which they start to spike according to the frequency and the strength of the contraction of the muscle. And no matter what, the spinal cord is going to release the contraction if the level of contraction goes too high that the muscles risk to rip off. You know when ripping off of muscles happen? I've seen it happening. When people train using only electrical stimulators and they don't reinforce their tendons. I know it's funny, but that's the case. So that is the most common diagram of physiological feedback for the muscles that I just explained through the muscle spindle. For amplifiers, it's the same. So the concept of feedback is to read the output, process it, and transform the output into an input. For amplifiers, we do the same. We read the output, we process it, particularly we attenuate it through resistor, and we put it back at the input. And this creates a way for us engineers to actually give amplifiers with well-defined and calibrated gain. If you know the gain of an amplifier, measuring the output, you can actually know what is the input precisely. That's the reason why it's known that EEG for specific task is that kind of amplitude in microvolts and so forth. So I'm not going to discuss all these details with you, of course. They are over there if you're interested to read the circuits, and you can shoot me an email if you need some clarification over there. But one little, well, that's feedback in general. Those are the benefit of feedback we can skip. Again, this figure, so I'm not saying to you that you should print this figure, laminate and bring it, put it in your wallet together with your beloved ones, but you just need to understand that amplifiers, they actually play a crucial role into biomedical or physiological recordings, because all the physiological signals, they are extremely faint, extremely small, and most importantly, some of the sources, they are protected by skin and tissues that we need to interface with, electrodes, pipette, needles, whatever it is, but we need to actually overcome all these possible source of noise and imbalances into the input impedance. So amplifier for physiological recordings, they need to have an extremely specific calibrated gain. They need to be ultra high input impedance because they need to withstand all this kind of possible issues arising by contact impedance imbalance between a number of electrodes. They need to withstand touch. I know this sounds weird, but amplifiers, the higher the gain of an amplifier is, the more an amplifier could be damaged by large inputs. Probably you're too young and you've never gone across this issue, but very old audio amplifiers, when you were connecting the microphone jack or the headphone jack, they were spiking, and that spike could actually destroy the speaker. So the recommendation was either to turn off the amplifier or put the volume down at the minimum. These days this is not the case. You know, you have your phone, you plug in and out the jack with no problems. For physiological amplifiers that the gain are order of magnitudes bigger than audio amplifiers, the fact that they don't destroy or catch fire every time you connect them to a participant, that means that there's something robust into the technology. So anyway, those are the principal characteristics that we want from a physiological amplifier. And one particular amplifier is what you're going to use and what you need to understand is the differential amplifier. I know this might sound weird, but all the recording you take or you're going to take are by difference. Voltages, they are measured by difference. There's no such a thing as an absolute voltage potential. Potential is always relative to a reference. That is why you take measurements using a different amplifier. You decide where your reference is. It could be the saline butt if you're doing some cellular electrophysiology recording, or in case of EEG, sometimes it's the tip of the nose or the linked mastoid or one or both the earlobes, all these kind of things. But every time you have a reference and you connect your reference to the negative input of your amplifier, and you connect the electrodes of interest to the positive input of the amplifier, so that you always do my signal of interest minus the reference. Now, Amplifiers, unfortunately, they are good. They could be good, manufactured fantastically well, but they aren't perfect. Particularly, if I ask you the difference between 13 and 10, or 7 and 4, the result is always 3, right? And in particular, no matter how many times I ask you, if I tell you what is the results of 7 minus 7, or 5 minus 5, or 3 minus 3, or 3.3 minus 3.3, the results is always 0, okay? Well, for a difference amplifier, sometimes the difference between two equal signals might not be 0. This is called common mode error. Okay? And in fact, if you go into the specs of your recording device you use, you're going to see this number. Well, this name. Common mode rejection ratio. And normally is expressed in decibel because it's a huge number. So decibel are a trick that engineers use to transform big number in small number. So to transform a decibel into the actual number, you need to make that number as a power of 10. And this gives you an idea of how big those numbers are. So the common mode rejection ratio, we want these things extremely high, ideally infinite. It's not the case. Sometimes it's in the order of 70 to 90 dB. If you want to have an extent of how big this number is, just transform using the relationship to this number into like 90 into a proper number with all the zeros. And I can assure you it's huge. But never the case, those aren't perfect. This is the reason why you can't appreciate sometimes in physiological recording very small measurements. Because if those small measurements, they touch the boundaries of your common mode rejection ratio, you are not sure if that is an artifact of the amplifier or is actual measurements. An example for EEG, evoked potential. When you flash something in front of the eyes of a participant and you record the EEG, you expect some responses into the brain due to the fact that there's this stimuli that from point blank happen. However, you can't see it if you do it just once. You need to repeat it many times. You need to record those EEG chunks, average it, and then you're going to have your evoked potential. Why? Because that evoked potential is so small, is fraction of microvolt, that is really at the boundary of the noise of the amplifier. Common mode noise, biasing, imperfection, and all these kind of things. The only way that you can show that that thing is real if you see it multiple times. That's why you do the averaging. I'm going to skip the instrumentation amplifier, which is just actually a better version of a difference amplifier. And that's what you use. Again, nobody expects from you to actually solve those circuits, but if you're interested in understanding those schematics and things, let us know. One other thing that you might encounter, the active electrodes. Active electrodes, they actually merge together amplifiers and electrodes to reduce the noise capture of wires. You have done EEG recording. You know what is going to happen if the participant move completely the head. And probably that's the reason why you have the wire that connected to the head, that they come from above the ceiling to avoid big movement. Because if you swing the wire, you're going to swing the traces. That is because charges going along those wires between the electrode and the amplifier, they could be as big or bigger than the signal itself. So you're going to amplify them and see them and maybe mistake them for signal. To reduce the kind of noise capture, and also to reduce the noise capture from the environment, like the 50 Hertz noise and the power line noise in general, you make the cable between the electrodes and the amplifier so short that you actually make the amplifier at the back plate of the electrode itself. And those are the so-called active electrodes, which they are really in fashion for EEG recordings, because EEG suffers of all possible way of noise capture. The shorter the connection between electrodes and amplifier is, the better it is. So there are a number of ways of making that. Obviously, I'm not delving into the details, but you just have to understand. And every time they give you electrodes or they give you probes of an amplifier and they say those are active electrodes, make sure that they are powered. Because the amplifier is inside the electrodes, and as now you know, amplifiers, they don't work if you don't power them. So as I said, there's so many of them. So for current sources, going back to stimulation, you need an amplifier as well. And you need an amplifier into a very well specified configuration called Holland pump circuit. Pretty funny is that this guy that invented this circuit thought that it was so trivial, he never patented it. He probably could have been richer than Bill Gates if he would have done it. Because he actually designed, using one single pump, a circuit capable of performing constant voltage and constant current of an arbitrary waveform stimulation. And that is not just used for human tissue stimulation, but for anything else into engineering. Now what I'm going to do, I'm just going to quickly go through a number of physiological signals that they require amplifiers, because the idea is that if you use those signals and you have a little bit of understanding of the signal, you can understand when is noise and when is actually signal. So the first of the signal is the electromyography, or EMG, which is the signal that you record from muscles. As I told you at the beginning of this lecture, muscles, they are connected to the spinal cord through nerves, and muscles, they are organized in fibers, and they can contract along the direction of the fiber only. So a small number of fibers in each muscle is controlled by one single nerve or axon, and the complex formed by the axon and all the innervated fibers is called a motor unit. So a motor unit is the quantum of energy that the muscles can exercise. If we want gross and strong muscle, like the biceps, the quadriceps, and the calf, probably you need only a couple of axons to, well, they are a bit more, but you don't need many axons to use those big muscles, because you don't need precision. Muscles inside the fingertips, instead, you have lots and lots of axons, because you want to be very precise with your fingertips. So that means that down to sometimes individual cells, they are controlled by one single axon. although individual cell control is the hard one. Anyway, the way that precision is achieved by muscles is a careful crafting of timing of contraction and number of motor units recruited every time. So EMG, the signals of the muscles that is used to assess how well or how strong a muscle is contracting, can be recorded by means of needles directly into the cells, into the muscle. And sometimes those needles, they are up to 20 centimeters in length. By as scary as it look, you won't feel them because those needles are very, very flexible and very, very thin. Or connection of skin patches. In any case, the EMG look like this. So these are recordings of single motor units. That means a very low contraction, so that the electrodes pick up the spike of those individual motor units that are spiking. The higher the contraction is, the more motor units are recruited and the faster they start to spike, until they become so fast and so many that you cannot distinguish anymore between motor units. In this case, this signal might look precisely like a noise. And it's very easy to mistake it by a noise, for noise. There's only one way, unfortunately, to distinguish between EMG, a peak contraction or a large contraction from noise. You need to observe the muscle or have other way of observing the contraction. For example, using accelerometer or other sensor that they can measure the vibration of the muscle. Because a muscle, when it contracts, vibrates. You can feel it if you put your finger on your biceps and you exercise a voluntary contraction as strong as you can actually feel small vibration happening inside the muscle. Those vibrations, they actually happen because, as I said, you are recruiting a big number of motor units, and you are making them to fire very fast. So what you feel under your fingertip is actually motor units that are contracting and relaxing, contracting and relaxing. Because you have so many organized like this, you feel like a vibration, like somebody's tickling under your finger pads. If you put a sensor on the muscle that is able to feel this kind of vibration, then you can relate the contraction to the vibration, and you know that what you are recording is actually not noise, but signal. Nevertheless, one good way of doing it is to start with small contraction. Even if you're doing stimulation, you start with a stimulation at low level so that you actually see and can distinguish individual motor units under the electrodes, and then you increase, and you should be able to observe this increase like is presented into the slide. Not going into the details of that, but in case you work with EMG, well, that is the little flowchart of interpretation of EMG signal. They are used for lots of things, but so shape of electrodes for EMG electrodes, as I said, needles. And needles, they are inserted orthogonal to the direction of the muscles I want to monitor. You can basically guess the orientation of the fiber of a muscle, observing, particularly for skeletal muscle, observing the direction of the contraction. The easiest one to see is the biceps. The fiber of the biceps, they run from shoulder to elbow into the direction of the bone, because the job of the biceps is to put the hand closer to the shoulder. No matter in which orientation the shoulder is, but the way you rotate the shoulder is other muscles, not the biceps. to record motor units into the biceps, you need to insert needles along going towards the bone. Because needles for EMG, they can carry up to 20 needle electrodes inside. As I told you, you don't feel it. Sure. Too much. You see the blood, but I can tell you, a lot of blood.
Paul was giving us a lecture last time and he kept talking about like the needles and I was
Oh, but that is only one needle. Come on, only one nerve. Imagine how many nerves you have inside the biceps or the quadriceps. I've done some recording of the quadriceps over here where we're inserting up to 20 needles into the participants.
I'm fine getting like if I get a needle, I'm fine. I don't like talking
But
about
thinking, okay,
yeah,
yeah.
I don't like talking about needles.
So, volume conductor for EMG, well, depends on what you want to observe. If you're doing some needle recording, you probably want to observe activity of the muscles, localize it. So that means that you're going to do difference between wires inside the needle referred to something else outside of the muscle. For example, one good way of recording EMG is to put the reference electrode onto the antagonist of the muscle. You know that muscles in the human body, they normally work as an agonist and antagonist, so they work in pair. When one contracts, the other one relaxes. So a good way of doing this normally is to use the reference on the one that is relaxed while you're doing the interesting measurements, which is the contraction. For example, for biceps, you might want to put the reference electrode at the triceps, at the back of the arm, because these muscles over here stretches when this one contracts. ECG, another interesting signal, the one that keeps us alive. That's very interesting because ECG is actually kind of recent. And the funny bit is, for electrophysiology, if you record ECG, you record ECG in voltage. If you happen that you go and talk with a cardiologist, cardiologists only understand ECG in terms of millimeters. And that is because originally ECG was recorded using that fancy equipment you see where the subject needed to have hands and feet into buckets full with saline solution to achieve low contact impedance. And the amplifier didn't exist at the time, so it was an electrometer, like a little needle that was moving with the charges from the body. And because these movements were so tiny, the movement of the needle, they were amplified by means of light and projected onto a photographic film, which was rolled at a certain speed and was told a certain number of millimeters. That is because doctors, cardiologists, they only understand ECG in terms of millimeter for both axes. So when they talk about heart rate, they just say, oh, how many millimeter there are between two heartbeats? Oh, how many millimeter the ECG of this patient is told? But anyway, that's where it comes from. So if you like, you can rephrase the ECG as a kind of way of measuring the development of technology And it started long ago because about 2,500 years ago, there are the very first documented piece of evidences that people actually try to describe the cardiovascular physiology and discover that at the center of everything there was the heart, the beating heart. I'm sure that these things was observed before by more ancient civilization, but the first written account we have is from about 2,500 years ago. So anyway, you can only learn things you can reproduce. So if you want to train a doctor or you want to do an experiment with electrophysiology, you need to compare your data with something that you know. And that is true particularly when you want to diagnose disease. Particularly the cardiovascular system, which can be affected by a number of diseases. How do you train doctor? So doctor skills in the past, they were related a lot from where they did their apprenticeship and where they did their traineeship in hospitals. Because what they were doing, they were going with senior doctor and they were trying to observe as many cases as possible to build their own experience. It was very recently, I think if I remember correctly, it's only about 400 years ago, that a doctor had the idea of transforming the pulse and the cardiac rhythm into music that you can actually play on a piano. In this way, he was able to transform into music sick and healthy rhythms, so doctors, medical students, they could train using just musical instruments. Because when you diagnose something about cardiac sounds, you're not interested into the specific kind of sound. You're interested only into the rhythm. To this extent, it doesn't matter if the rhythm is made using a drum or a piano or whatever. So the ECG came only about 100 years ago and is actually the electromagnetic representation of the activity of the heart, which is related to the mechanical activity of the heart, of course, but the mechanical representation of the activity of the heart is something else. So that's what Dr. Michel Bertrand Valentini did about 400, 500 years ago to represent and train people with it. Those are other kind of representation and experiments to actually link the heart to the circulation and everything. And that's how they came to the discovery of the electrical activity of the heart being linked to the actual activity, mechanical activity of the heart. So a survivor of a terrible chest and breast cancer needed to have part of her chest removed to remove the tumor, left her heart exposed by a thin membrane. So doctor, using that fancy device I showed you a few slides ago, they were actually observing the deflection of the needle together with the physical look at the beating heart. That's how the link was made. And the first ECG device needed to have electrodes on the tongue. Not very pleasant, because that electrodes are actually big pliers. Why? Because we needed to achieve very low contact impedance, because the input impedance of the amplifier at the time was terrible. Now we use different system. There are different models, representation of the volumic conductor of the heart. Not going into much details of that. That's the physiology of the heart, and as I said before, those are the sinus node and atrioventricular node, and how they beat and which speed they beat. We discussed about the pacemaker cell, and now we can watch this animation that shows how the heartbeat is generated by the sinoatrial node and how it propagates through action potential going in through the heart until it reaches the atrioventricular node and make the ventricular to beat and form the characteristic standardized shape of PQRST waveform, where all those colors now make sense with the colors of the action potential generated and the part of the heart that they gets activated according to the color into the chronology of time of these waveforms. I'll skip this. I'll skip all of this because, well, I'm a fan of this picture. I don't have it. I don't need it to have any more in my wallet laminated because I know it. But at the beginning, I had one. So, amplifier specification for ECG. Well, you can see that all these things, they need to be, these things are common, and probably for you that you use an EEG device, you can go and check those specs for the EEG device. You probably will see that they specify the common mode rejection ratio. They might or may not specify the input referred noise. For an EEG device, they will, because it will tell you basically how many trials need to average to record properly the event-related EEG or evoked potential. The input impedance is clarified. What is the largest signal that the amplifier can amplify correctly? And what is the largest signal that can be given to the amplifier without the amplifier catching fire or exploding? In case of an ECG device, has to be more than 400 joule per second because they need to withstand the defibrillator pulses. If it's an ECG monitor, manufacturers assume that it could be used during resuscitation. So the amplifier has to withstand that. So I told you, and of course, frequency parameters. So what's the bandwidth? That has to cover the bandwidth of signal of interest. So this goes referred to that figure that I mentioned. So I told you that every time you put a patient or a participant in contact with an amplifier, you put it at risk. The reason is the leakage currents. So we don't realize, but the simple fact that we have something connected to the main, like a computer, will create some accumulation of charges and leakage of current from the power source onto the chassis of the device. Because we have a skin and probably we wear shoes and everything, those things are safe to touch, even when they have a metal case. When you have electrodes, particularly needles or catheters, so something that is inside of the body, you are not protected anymore from those things. Experiments show that if the skin barrier is intact, even hundreds of milliampere of leakage current over devices, they're safe. In case of electrodes, ECG, EEG recording, because you create a preferred pathway to go inside the body, because you're actually probing the signal inside of the body. 200 microampere is the safety threshold.